Alrighty, welcome back. Now let's go ahead and get into how to draw Lewis dot structures of ions, of expanded octets, and how to use formal charges. So to start, our fifth rule for Lewis dot structures, so this is a continuation of the last video, for molecules with an overall charge, so an ion, electrons should be taken away or added based on their charge. So if a molecule is positive, electrons should be taken away because we're losing a negative charge. So we should take it away, and we should take it away from the lowest electronegative atom. So usually this comes from the central atom. So in this case, we have nitrogen and hydrogen, and we have a positive charge. That positive charge, we're going to actually leave nitrogen alone in this case. We're going to leave it alone, but we're going to take one hydrogen and remove its electron entirely. Just going to remove its one electron. The rest will remain the same. So those all remain the same. But these two electrons, they still need to, they make a bond with that. So rather than them sharing electrons, those two non-bonding electrons are actually being donated to the hydrogen and then shared that way. So at that point, nitrogen looks more, oops. So that hydrogen was a positive charge, but now our nitrogen is the one that is positively charged. So nitrogen, now it's the positively charged one because we took electrons away from it, and it's no longer having as many electrons. So there's a positive charge there. And we'll talk about how exactly that is when we get to formal charge. Now, if the molecule is negative, if the overall molecule is negative, electrons should be added to the atom with the highest electronegativity. And this is usually an atom on the outside, so not the central atom. In this case, we have CO3 with a 2 negative charge. We're going to leave carbon alone. We're going to leave one oxygen alone. But for two of those oxygens, we're actually going to add a negative charge, an extra electron. And so we make a bond there, make a bond there, and then we make two bonds with that one because those have things left over. So overall, our CO3 2 negative would look something like this. And I'm putting those negative charges because I want to make sure to write down where they are in the atom. Now, expanded octets. These are any kind of element, phosphorus, sulfur, or anything beyond that on the periodic table. The octet rule is not as widely applicable as it would sound, given the name octet rule. It actually only applies to anything before phosphorus and after boron. So a very limited amount of atoms, but it's still useful when talking about those atoms. Here, however, it's not. These elements don't always have an expanded octet. It's just if there are more unpaired electrons on the outside atoms than on the inside, they will pair more. So in this case, we have silicon hexafluoride, or nope, sulfur hexafluoride, SF6. And we are going to put silicon there, or sulfur there in the middle. We have 6 fluorines that we need to make. This is going to take a bit of time. This is the annoying part about group 17 atoms, is they just take so long to make because of all of those electrons. Now, as you can tell, we have two pairs of electrons and 2 single electrons on sulfur. But we have 1, 2, 3, 4, 5, 6 unpaired electrons on the fluorine. So each of those electrons on the sulfur are actually going to bond with the fluorines on the outside. Oops. So bonding here, bonding here, bonding here, bonding here, bonding here, and bonding here. And so they are left with sulfur. I'm going to neglect all of the electrons on the fluorines just for speed, but know that there should be 6 electrons in addition to the single bond on each of those fluorines. Now, last but not least, let's talk about formal charge. Formal charge is the charge assigned to an atom in a molecule, assuming that electrons in all chemical bonds are actually shared equally between those atoms. Now, to use formal charge, we actually want to use them to check our answers. And this is where those charges before on the first 2 problems actually came from. The way that we use these to check our answers is we want to make sure that it doesn't violate 2 common rules. Not all of them follow this. There are a couple exceptions, but for the most part, these always stand true. The central atom, first off, the central atom should always have a formal charge of 0. And there are few exceptions of that, but typically that is the case broadly. And then the formal charge of each atom should add up to equal the charge of the molecule. So overall, each atom, when you add up their formal charges, should equal the charge of the atom, or of the molecule overall. In order to calculate formal charge, it's the number of valence electrons of the atom in its elemental form, minus the number of non-bonding electrons on the atom in the molecule, the way that you've drawn the molecule, minus the number of bonds. So let's go back and actually calculate this for each of our atoms in the molecule. So let's start with hydrogen. Hydrogen has 1, so we're talking formal charge here. So Fc. Hydrogen only has 1 valence electron. So 1 minus, it doesn't have any non-bonding electrons. There's no dots around the hydrogens. Minus 1 bond, so that's equal to 0. And so that is true for each one of these hydrogens. So we don't need to do it more than once because these all are the same. They're all single hydrogens bonded singly. There's no electrons on them. Then if we try the nitrogen, formal charge is equal to, nitrogen typically only has 5 valence electrons based on where it is on the periodic table. It doesn't have any non-bonding electrons, and then it has 4 bonds on it. So it currently has a +1 charge. So that's where that +1 came from at the start. That +1 was its formal charge. I just didn't give you a name for it yet. Now, this is the one exception that I could think of for that central carbon, central atom being 0 charge. This is the one exception that I could think of. Now, what about here? So we have, let's check our central carbon, our central atom. That carbon has, so formal charge equals 4 valence electrons minus no non-bonding electrons minus 4 bonds. All right, carbon's got a 0 charge. We're good there. Now what about our atoms here? So our oxygen here, we have typically 6 electrons, 6 valence electrons. Now we have 6 electrons around it, as well as 1 bond. So it's got a -1 charge. So again, I told you the charge, but it was actually the formal charge, just because of its excess of electron. And now that also applies to the other electron over here. That applies over here as well. But we need to do one more, that other oxygen. It's different than the other two. So this oxygen, it has a formal charge of, typically oxygens have 6 valence electrons, minus 1, 2, 3, 4, 4 non-bonding electrons, minus 2 bonds. And so that would be a 0 formal charge. Now, same thing can be done here for all of these atoms. So again, we assumed that there were 6 pairs, or 3 pairs of electrons, or 6 electrons. I just didn't want to draw all of them in. 6 times 6 would be 36 dots that I would have had to draw on camera. That's too much. So formal charge, fluorine typically has 7 valence electrons, minus 6 non-bonding electrons, minus 1 bond. Each of the fluorines has a 0 charge, so that's good. What about our sulfur? Sulfur's formal charge, sulfur typically is 6 valence electrons, minus no non-bonding electrons, minus 6 bonds. It's got a 0 charge. So our central atom has a 0 charge. We are good to go. Now we've done NH3, we've done these 3. Let's try 2 more on our own. So compiling it all together. So we start with chlorine and O2. So Cl, 1, 2, 3, 4, 5, 6, 7. And then oxygen, 1, 2, 3, 4, 5, 6, 7. So that's going to be our negatively charged oxygen. I sort of jumped ahead there, but since we have a -1 charge overall, one of our oxygens, which are the more electronegative, has to have that extra electron. So rather than oxygen normally having 6, this is going to have 7. But the other oxygen is going to remain having 6 electrons. Now here, this is an example of so once we make our bond, our central atom has no more non-bonded it has non-bonding electrons, but they're all paired. However, there's still things to be bonded. So one of those pairs has to be broken up. And so we're given that chlorine still has 2 pairs of electrons, but it's double bonded to 1 oxygen, and then it is singly bonded to the other oxygen. Now let's do our formal charges. Formal charge of this one, again, 6 for oxygen, minus 4 non-bonding electrons and 2 bonds. We've got a 0 charge. Our chlorine, that's the one that we really want to know. Does it have a 0 charge? That's important. Our formal charge is equal to 7 minus 4 non-bonding electrons minus 3 bonds. That is a 0 charge. So we're good there. And then, of course, we should already know that it's a -1 charge based on this, but let's check. Let's check our answer just to be doubly, triply sure. So oxygen typically has 6 valence electrons minus, well, it currently has 6 non-bonding electrons minus 1 bond. It's got a -1 charge. Now -1 plus 0 equals -1. We are good to go. Everything adds up. And then last but not least, let's do BrO3. So again, BR. Ooh, I was about to just rewrite BrO3. Now I'm going to do, so we have 3 oxygens this time, but still one of them has to have a negative charge. We let this one earlier have it. Let's have the one on the right have it. And so that's got a negative charge now. Let's start bonding. Oh, well, we ran into a problem. We no longer have non-bonding, or we no longer have electrons to bond with the center atom. So we're going to have to start splitting up some of these pairs. So let's actually split this pair up to bond here, and split this pair up to bond here. Now the only reason why we can do this is because bromine and before that chlorine are both extended octets. They can extend their octets, meaning they can accommodate more than 8 electrons in the center. This cannot happen for anything before phosphorus on the periodic table. So carbon can't do this. Fluorine can't really do this. Oxygen can't do this. None of those in that second row. Now that we have this, let's do BR. All right, so we've drawn our thing. Now these 2 oxygens are equivalent. So let's calculate our formal charge of both. So the formal charge of these 2, oxygen has 6 valence electrons, minus each one of them has 4 non-bonding electrons. Each one of them has 2 bonding electrons, or bonds, rather. So 6 minus 4 minus 2 is 0. So those 2 are 0. Is our center atom 0? Let's check. So the formal charge of bromine, we have 7, because bromine has 7 valence electrons, minus 2 non-bonding electrons, and 1, 2, 3, 4, 5, minus 5 bonds. We got 0. And then last but not least, we have this oxygen. Formal charge equals 6 valence electrons minus 6 Non-bonding electrons minus 1 bond. That is a -1. So 0 plus 0 plus -1 equals -1. So we are good. Hope that helped.